with one more flipped classroom video. 3 tips before we start. You can always speed up or slow down this playback speed if that helps you get through the video. Second, you can pause the video at any time and catch up on your notes. Last, you can turn on the captions and watch my words go by on the bottom of your screen. Today's video is a review of our chapter on three-dimensional geometric solids. So if you remember, we did picky little calculations inside figures, then we calculated the volume of such figures, and then finally we calculated the surface area, which was the most complicated process that we did. So let's start with this word problem. Notice there's no diagram, so your first step is going to be to draw that diagram. A rectangular box measures 3 centimeters by 6 centimeters by 11 centimeters. So we've got this box, those are the measurements. Will a 13 centimeter pencil fit completely inside the box? So think about what that means for a sec. Okay, so you've got to drop that pencil in the box and jiggle it around so that it has the greatest chance of fitting completely inside. Like imagine if there's a top, we needed to put it on the top and the pencil has to be completely inside. All right, so now I want you to pause the video and draw a diagram that's going to help you solve this problem. All right, so here's my box, and I just labeled it 3 by 6 by 11. Not quite to scale, but it will totally work for our problem. So now I want you to think, what length do I need to calculate in my box? Okay, so think about putting a pencil in there the way that it will have the best chance of fitting. So pause the video and think about that. If you know if you know where you're going to put the pencil, go ahead and make a line in the box that shows that length. Okay, check it out. It's going to be a diagonal from one corner to the opposite corner. So it could be any one of these 4 diagonals that we have. I'm going to do it with the one that's kind of easiest to see. So that would be this one. So it's the front top corner to the back bottom corner. And that gives us this triangle also. So we have that triangle, and then we also have this base triangle. So I'm going to mark some right angles. That's a right angle, and so is that. Right there. Okay, so now if you're feeling bold, pause the video and answer the question. Now we've done this calculation a bunch of times already. I just made it more difficult by starting with a word problem and no diagram. So you had to do some critical thinking to figure that out. So here we are. We're trying to calculate this diagonal of the box, but we can't use the Pythagorean theorem right away because we don't have this base length. Remember, we have a triangle right there, the hypotenuse of which is the diagonal that we're after. But we don't have this length here. But fortunately, that length is the hypotenuse of the triangle that you can make with the base. So I just did my 3 and my 6 right there, and I just labeled that C. That's this diagonal going along right there. I did my math. C is the square root of 3 squared plus 6 squared. That gives us 6.71 centimeters for the base of this bigger triangle. So now pause the video and finish the calculation. Okay, so here's what I get. I just broke out this little triangle. That's the triangle that the hypotenuse is our diagonal. I labeled it diag, and I have 11 and 6. So I solved that for the diagonal, 11 squared plus 6.71 squared. I got 12.9 centimeters. So answer the question, does the pencil fit? Nope, it's just a little too long. 13 centimeters, 12.9 centimeters. So not quite. Now, if you want a little extra practice, go ahead and calculate the volume and the surface area of this box. All right, in case you tried those 2 calculations I suggested you do, and you should do those as practice, I get the volume of that box. That's just length times width times height. Boom, boom, boom. I get a volume of 198 cubic centimeters. Surface area is a little bit more complicated. You have 2 times the face that's 3 by 6, plus 2 times the face that's 6 by 11, plus 2 times the face that's 3 by 11, and I get 234 centimeters. So you want to give that a practice. Right, I want to do another one of those nitpicky calculate something inside a 3-dimensional solid problems. So here we have a cylinder, marked some things on there. We've got a 30 centimeter height from the center of the top to the center of the bottom, and we've got a 9 centimeter radius of our cylinder. Okay, so that pretty much describes the cylinder. We should be able to calculate anything we need at this point. All right, so here's the question. Find BD. Okay, I'm going to switch to red here. BD is this line here going across from this point on the edge to this point on the edge. Now, it may seem at first like you just don't have enough information, but you do. So if you're feeling bold, pause the video and see how far you can take this calculation. Okay, now your first step here is to recognize that you have an isosceles triangle that you can use. And understanding how to do that is super important. So take a look at this triangle down here, the BOD triangle. In fact, we're trying to find this side of that triangle. You notice that we have a radius of our cylinder is 9. Well, that's also a radius. So we know that this one is also 9 centimeters. So now I'm going to take this triangle and draw it out here. Make it nice and big. Label it up. B-O-D, like that. Now let's go ahead and put in the angle we know. This is 132. And then the sides we know, 9 and 9. Okay, now you might be thinking, that's still not enough information to calculate BD. And you're right, but we can deduce the information that we need. So check this out. An isosceles triangle, two sides are equal. That means that the angles opposite of those sides are also equal. So that's going to allow us to find out what those angles are. Remember, triangle has 180 degrees, so we can subtract 132, and that's going to give us 48. So 180 minus 132 gives us 48. Now that 48 is going to be evenly spread between these two angles because they're equal. So this is 24 degrees here, and that's 24 degrees there. Now we have enough information to find BD. Now this formula that you're going to need is in your formula booklet, but you have to notice that you can use it and remember how it works. So think a minute. If you want to really get the most out of this video, go to your formula booklet and see if you can find that formula. Okay, so here's the thing. This is the sine rule. Remember how we have A over sine of angle A, which is opposite of side A, is equal to B over sine big B, which equals C over sine big C. So that's the sine rule. It's just a ratio, and it allows us that if we know 3 of the 4 things in any one of the pairs, we can find the 4th thing. And you'll notice here that we have an angle over a side. This is the side we want, but now we have an angle over a side, or the other one, which is the same. So now that you've seen all that, pause the video and see if you can write down a ratio equal to another ratio that has 3 knowns and the one thing that you need to find. Okay, so let's take a look. What we've got is BD, that's what we're after, over sine 132. And now I'm just going to pick this side. So that's going to be 9 over sine 24. Now we have 3 knowns and 1 unknown, so we can easily figure this out. I'm going to multiply this up to the 9 and get BD equals 9 times sine 132 divided by the sine of 24. I want you to go ahead and pause the video, do that calculation, and see what you get. So when I get that, I get BD is 16.4. Now, I always like to do a little reality check. Take a look at my figure. Even though it's not drawn to scale, that should make sense. And check it out. If these two are 9, and that's 134 degrees, that's a pretty wide angle, like we've drawn that, it really does make sense that this could be 16.4. Let's say you got 2. You should think about that. It's probably not 2. Let's say you got 150. Probably not 150. That's just way too big. So I like to do a reality check like that, especially when you have a figure, because you can see what the sides are. All right, let's do a volume problem. Here's a cone, okay? So find the volume of this cone. You're given 2 measurements. The radius of the cone, the radius of the base is 1.5 cm, and then this distance here along the outside edge of the cone is 4.7 centimeters. So go ahead and pause the video and see if you can figure out the volume. But first, let me just remind you of the volume formula. All right, so if you plugged this in for h, you got a bad result, okay? This is the slant height. The h that we're after is this height, from the peak to the center of the base. So we have a side calculation that we need to do first before we can do our plug-in with the volume formula. So check it out. I've got a little mini triangle, which I'm just going to sketch right here. And there's our radius is 1.5. We don't know our h, and our slant height, which is the hypotenuse, is 4.7. So now we can do this. We have h squared plus 1.5 squared equals 4.7 squared. So now we end up with h equals the square root of 4.7 squared minus 1.5 squared. Now that's going to give us our h. Go ahead and do that calculation. All right, so here's what I get. I get 4.45 centimeters for the height of my cone. Now go ahead and pause the video, do the plug-in, and find your volume. All right, here's my plug-in step for the volume calculation. 1/3 pi times r squared times the h. And when I run that through my calculator, I get 10.5 centimeters cubed. Remember, your units need to be correct. Okay, let's do a more complicated volume calculation. So what I've drawn here for you is a grain silo. Okay, so this is what we use to store like corn in the Midwest, and they're quite large. They hold lots of grain, and we're going to calculate the volume of it. So we have all the information here. We're going to use two formulas. We're going to need the volume of a cone and the volume of a cylinder to do this calc. So I would like you to, if you're feeling super bold, just go ahead and do the whole calculation. See how far you get. All right, let's tackle the cone first. So I added a little bit to my cone. I added the cone's height here, and I just transposed the radius for the base of the cylinder up to the cone because they share the same base. So that information is going to transfer over. And so then I drew my little side triangle representing this triangle because I need to find the h. This h in the cone volume formula is not the 185. That is the slant height, which we use for certain things, but not for volume. So I came up with my little right triangle to figure that out. And what I've got is h squared plus 45 squared is going to equal 185 squared. So h is going to be the square root of 185 squared minus 45 squared. So go ahead and do that calculation. All right, so I did my math and I got 179 meters for the volume, or for the height. That's this height of my cone. I'm going to go ahead and write that here. Now we need the volume of the cone. So you have your formula there. Go ahead and do the plug-in step and do your calculation. All right, so my volume of my cone, I did my plug-in step there. 1/3 times pi times the radius squared. There's my radius, 45, times my height, which is 179. And I get 379,583 meters cubed. Now I'm keeping all my digits here because I'm going to go to 3 sig figs at the very end of this calc. All right, real quick now, let's calculate the volume of the cylinder. Here's my formula, pi r squared h. You've got all your information on the diagram. Go ahead and put in the information and do the calc. Okay, so here's my plug-in step, pi r squared. Again, same radius for the cone as for the cylinder, times the height, this time the height of the cylinder, and so that's my 200. When I punched it into my calculator, I got 1,272,345, and I wrote centimeters. It's meters cubed. All right, so are we done? That's a big nope, which wants the total volume of the silo, so I have to add my cone volume to that. That's 379,583 meters cubed. Go ahead, get out your calc and figure that out. When I do that calculation, I get 1,650,000 cubic meters. Now that's a lot of volume in there. Now just know that the IB might have asked the question this way. They might have given you all the information. They might have told you how many kilograms a cubic meter of grain weighs and asked you to calculate the total weight of the silo when it's filled with grain. So just remember that they might bury these kinds of calculations into a word problem that you have to figure out and then do the right steps. All right, we're going to keep this diagram, but now we're going to find the surface area. And this is a little bit more complicated. Please pause the video and do some thinking And if you think you can see your way through that with the various formulas, go ahead and calculate the surface area of this silo. So as a first step, because I'm methodical, I like to write lots of steps, you know that about me, I just came up with my two formulas. So the surface area for a cone is pi r squared for the base of the cone plus pi rh, which gives you the surface area of the curved surface of the cone. So there's a surface area of a cone. Now here's a surface area of a cylinder. It's 2 pi r squared because we have a bottom base and a top base. So that's the area of the bases plus pi rh, which is just the curved surface that wraps around the cylinder. So these are our two surface area formulas that we're going to need. However, we need to do something to that before we start calculating. Pause the video and think real hard. Okay, check it out. This base, which is the top of the cylinder and the bottom of the cone, is not there. Okay? The silo stops here and then goes to a point. So the cylinder stops and then we have the cone beginning. But there's no base for the cone and there's no base for the cylinder. Okay, so our surface area, and let's just go ahead and make that, surface area silo is going to be, now pause the video again and see if you can use these two equations to write the correct formula that will get us the surface area of the silo. Okay, here's what we get. Since the cone base is not part of this calculation, all we need is the curved surface, which is pi rl. So that's the first part that we're going to calculate. Now for the cylinder, we do have one base, just not the other. So instead of 2 pi r squared for two bases, I just have pi r squared for one base. And then finally, I need the curved surface of the cylinder. That's entirely there in the silo. So that's pi rh. Now go ahead, pause the video and do that calculation. All right, I broke it down for you, so in case you made a mistake, you could troubleshoot that. Our three values are for pi rl, I get that. For pi r squared, I get that. And for pi rh, I get that. Adding them together, going to sig figs, I get 60,800 cubic meters in the silo. What if the question was, how much paint is required to cover the outside of the silo? And what we would give you is like 1 liter of paint covers like 1 square meter, or maybe it would be a little harder than that, like maybe 10 liters of paint covers 22 square meters. And so the whole question would be, here's the picture. How many liters of paint is required to paint the outside of the silo? Now that you've watched the video, take a moment to jot down any questions so you can bring them to our next class. Remember that you can always watch the video again to deepen your understanding. If you enjoyed the video, please click like or subscribe.